In January 2006, a small piano-sized spacecraft left Earth faster than any human-made object before it. 9.5 years later, it screamed past Pluto at 31,000 miles per hour. And by the time it called home, the engineers who had launched it were nearly a decade older. That was just our own backyard. Tonight, we're going to do something honest. No warp drives, no hand-waving. We're going to ask exactly how long it would take to reach 3 destinations using the technology we have, the technology we could build, and the absolute speed limit the universe allows. Pluto, Proxima Centauri, and the edge of the observable universe. The answers stretch from years to centuries to numbers that break the human imagination. Let's start with the easy one, Pluto. In 2006, NASA launched New Horizons, the fastest spacecraft ever to leave Earth at that point. It departed at roughly 36,000 miles per hour relative to Earth, fast enough to cross the Moon's orbit in just 9 hours. Apollo 11 took 3 days to do the same trip. And yet, even at that blistering speed, New Horizons needed 9 years and 6 months to reach Pluto. It got a gravity assist from Jupiter in 2007, which boosted it by another 9,000 miles per hour. It still took nearly a decade. Why? Because Pluto, on average, sits about 3.7 billion miles from the Sun, roughly 40 times farther from the Sun than Earth. To put that in perspective, light itself, the fastest thing in the universe, takes about 5.5 hours to travel from Earth to Pluto when the dwarf planet is at its average distance. Radio commands sent to New Horizons during its flyby took over 4 hours to arrive. Mission controllers had to plan every maneuver days in advance, then wait, knowing the spacecraft was already alone, executing decisions made in the past. Could we get there faster? Theoretically, yes. NASA's Parker Solar Probe, currently the fastest human-made object in history, has reached speeds of around 430,000 miles per hour as it whips through the Sun's corona. According to NASA's mission data, that's more than 10 times faster than New Horizons. If you could somehow point Parker Solar Probe at Pluto and maintain that velocity, you'd arrive in roughly 11 months. But there's a catch, and it's the same catch that haunts every conversation about space travel. Speed isn't free. Parker is fast because the Sun's gravity is pulling it in. To reach Pluto with that kind of velocity, you'd need to accelerate the entire way out, fighting the Sun's gravity instead of falling toward it. With chemical rockets, that's effectively impossible. You'd run out of fuel long before you ran out of distance. This is the first hard truth of interstellar travel. The cosmos isn't measured in distance alone. It's measured in fuel, in patience, and in human lifetimes. Now let's leave the solar system. Our next target, Proxima Centauri, the closest known star to the Sun, a small red dwarf sitting 4.24 light-years away. According to ESA and ESO observations, it hosts at least one rocky planet in its habitable zone, Proxima b, discovered in 2016. A light-year is the distance light travels in a year, about 5.88 trillion miles. Proxima Centauri is 4.24 of those. So if you could travel at the speed of light, you'd arrive in just over 4 years. But you can't. Nothing with mass can. So how long does it really take? Let's start with what we already have. Voyager 1, launched in 1977, is currently the farthest human-made object from Earth, over 15 billion miles away, traveling at about 38,000 miles per hour. It's already in interstellar space. But Voyager isn't aimed at Proxima Centauri. And even if it were at its current speed, it would take Voyager roughly 75,000 years to cover that distance. 75,000 years. To put that in human terms, when Voyager arrived, the descendants of the people who built it would have evolved past the point where modern humans first left Africa. Empires would have risen and fallen hundreds of times. Languages spoken at launch would be unreadable. So, we need something faster. In 2016, physicist Stephen Hawking and investor Yuri Milner announced Breakthrough Starshot, a concept to send tiny gram-scale probes to Proxima Centauri using ground-based lasers. The idea, as published in their initiative documents, is to accelerate microchip-sized spacecraft to roughly 20% the speed of light using a 100-gigawatt laser array pushing on light sails. At that speed, the journey would take about 20 years. Add another 4.24 years for the data to come back, and humanity could receive close-up images of an alien world within a single human generation. But Breakthrough Starshot is, for now, a concept. The engineering challenges are immense. The lasers don't exist at that scale. The probes would need to survive interstellar dust at relativistic speeds, where a single grain of sand has the energy of a hand grenade. And these probes wouldn't carry humans. They'd weigh less than a paperclip. For a crewed mission, the math gets darker. Even with advanced fusion propulsion, a technology we don't yet have but is theoretically plausible, studies like Project Daedalus from the British Interplanetary Society in the 1970s and its successor, Project Icarus, estimate journey times of around 50 to 100 years to reach Proxima at a fraction of light speed. Anyone who left Earth would be saying goodbye forever. And here's where physics gets strange. According to Einstein's special relativity, confirmed by countless experiments since 1905, time itself slows down for objects moving close to the speed of light. If you could travel at 99.9% the speed of light, the trip to Proxima would take about 4.25 years to outside observers, but only about 2.5 months would pass for the crew on board. That's not science fiction. That's measured fact. GPS satellites have to correct for relativistic time dilation every single day, or your phone would lose its location within minutes. The faster you go, the less time you experience. The universe rewards speed with time itself. But there's a price. To accelerate a spacecraft of even modest mass to 99.9%, the speed of light requires energy that by some calculations exceeds humanity's entire annual energy production by orders of magnitude. We don't lack the equations, we lack the power. Now for our final destination, the edge of the observable universe. According to data from the Planck satellite and published in collaboration between ESA and NASA, the observable universe extends about 46.5 billion light-years in every direction from Earth. That's the distance to the most remote light we can detect. The cosmic microwave background, the afterglow of the Big Bang, released about 13.8 billion years ago. Wait. If the universe is 13.8 billion years old, how can we see things 46.5 billion light-years away? The answer is one of the strangest facts in cosmology. Space itself is expanding. The light from the most distant galaxies started its journey when the universe was small and hot. But during the billions of years that light traveled, the space between us stretched. The galaxies that emitted that light are now much farther from us than the light's original travel distance. So, how long would it take to reach the edge? Here's the twist that breaks the question. Even at the speed of light, which, again, we cannot reach, we could never get there. The universe is expanding at an accelerating rate, driven by what cosmologists call dark energy. Galaxies beyond a certain horizon are receding faster than light can travel toward us, not because they're moving through space faster than light, that's forbidden, but because the space between us is itself growing. According to research published in monthly notices of the Royal Astronomical Society and elsewhere, only about 3% of the galaxies in the observable universe are still reachable, even in principle, by a beam of light, leaving Earth today. The other 97% are already gone, locked behind the cosmological event horizon, drifting away forever. In other words, the answer to how long to reach the edge of the universe is not a number. It's a closed door. Even infinite time and infinite speed, bounded by light, would not be enough. So here's where we stand. Pluto, with current technology, about a decade. Proxima Centauri, with technology we might build this century, anywhere from 20 years to 100, and the edge of the observable universe, never. There's something humbling about these numbers. Not depressing. Humbling. We are tiny creatures with short lives on a small planet around an ordinary star in a universe that may simply be too vast for us to ever fully visit. And yet we have built machines that touch Pluto. We have pulled images from the edge of cosmic time. We have measured distances we cannot cross. The reach of human curiosity is, in its own quiet way, infinite, even when our rockets are not. If this journey moved you, subscribe. There's more to see. At the cosmic edge,